Okay, so a lot of the work you'll tend to do in Python will be more focused on making use of algorithms. Of course, you can do this just as much in R. It's just that Python gets used for applications that tend to be more big data applications, and so I'm going to reasonably kind of make emphasize the things that the kinds of processes we tend to use for big data applications here. Okay, so whenever you're using an algorithm, it's very important that you think about the computing resources that you're going to use. If you have one if you're trying to solve some sort of problem and you don't think very clearly about the efficiency of your algorithm, you're going to have trouble effectively finding a solution that'll run efficiently and will execute in a timely manner to where you can really use the results. So we're going to talk a little bit about, we're going to write an algorithm here. We're going to talk about analyzing the computing resources required, the time required of the algorithm, but also memory usage. Maxing out memory in both R and Python is still pretty easy to do. I find it's easy to do on at least a monthly, if not weekly basis. And so thinking about efficiency as we go through these different kinds of algorithms is really important. We're going to go through a few approaches here to just perform a certain task or solve a certain problem, and then we'll make a comparison at the very end to think about efficiency. Kind of much like what we do when we wrote our did our calculations in R. Just a similar approach here. So here, the problem we're going to solve is something called the maximum segment sum. So we're going to go through here and make sure we conceptually understand the problem first, and then we'll look at some first attempt algorithms and then improve. So the input on this algorithm is going to be a list of integers. It'll just be a list object. It's going to contain a bunch of integers, and the output is going to be the maximum sum of any segment. I should say consecutive segment. And a segment is just a slice of a list, a contiguous portion. So I should have said contiguous before I said consecutive, which is kind of the right idea, but not exactly. But a contiguous portion of the list. So for example, if we had the list -4, 2, and 6, the segments are, of course, the empty set, but that's not very interesting for us here. The individual singletons, -4, 2, 6, and then the contiguous sets of size 2. So -4, 2, and then 2, 6. Notice we don't have -4, 6 because that's not contiguous. And then the full set. And the maximum segment sum is going to be the 2, 6. Because notice, if you add up 2 and 6, you get 8. If you go through any of these and add up the elements of your list, let's see, the next highest is just the singleton 6. And then the next highest is this one here, because you're going to get 8. I'm sorry. You're going to get 8 minus 4, which is 4. And then after that, you've got 2, -2, and -4, if we ordered all the segment sums. Okay? So this is very useful. I do this sometimes, this kind of procedure for an algorithm I've written in the past where I'm looking at these partial orderings, and so you sometimes need to do these kinds of calculations for that. Okay, so let's move on. Pretty simple problem, but how do we do this efficiently within Python? Oh, let's practice. I forgot. What's the maximum segment sum of the list? I'm going to have to calculate it here. Give me a moment. I'll pause and make sure I get this right. Okay, I pretty quickly went through and, I mean, you can break it down to 2's, but pretty quickly you see, okay, you're not getting very big numbers. The biggest here is 4 with -6, 2. Adding in the 8, you're going to get 12, right? And I can't find anything bigger than 12. So 8, negative 6, 10 gives you 12, which I believe is your maximum segment sum. Okay, what about this list? What's the maximum segment sum? Oh, wait. That's the difference. So let's go back through, think about what it could be. I think here, you're going to have to go to a singleton, aren't you? So 10, just the single number. Okay, segment observations. The maximum segment sum, or the list of all positive numbers, is the sum of all those elements in the list. Plus, you're going to need to get all those sub-lists, okay? So this gets kind of tricky. When we have negative numbers in the list, it gets trickier. Which ones do we include? If all numbers are negative, the maximum sum is 0 from the empty segment, okay? So if we can check every segment of a list by pairing each possible starting point with each possible ending point, then that might be the best way to go about it. So let's take a look at this. Approach A. This first approach is going to compute the sum of each segment in the list and compare it to the maximum so far. So we're just going to go through the whole list and then retain the maximum and keep that saved as like a variable, a value in a variable, and then see how, if it needs updating at any point. So we're going to name a variable max, all right, make it 0 because that's going to be our minimum here. We go through, our first segment is 4. Well, automatically we change because 4 is bigger than 0. Then the next segment is 4, negative 3. We get 1, so it does not change. Then we get 4, negative 3, 9. That becomes 10, so it changes to 10. Then we sum all of them up. We get 5. Well, it remains 10. Then we're going to start off at 3 and then go 3, 9, 6, and so forth. Okay? Do you see how it goes? We'll go through. This will be 0, I'm sorry, it's going to be 1. Then we start off at 9. Well, 9 is not bigger than 10. We know we're not going to get anything bigger than 10 by the end, okay? Okay, so this is going to work through our list. So notice the input is list. We're going to take in a list of integers, and the output or the return value will just be another integer, which returns the maximum segment sum of the list. So we start by initializing our maximum so far. We go through the elements of our list, and we have to keep track of the upper and the lower. So we have here the lower value, where we begin in the range of the list, and then the upper, which begins in the lower value up to the length of the list. Okay? Here we initialize a value for sum after we've started with a first upper and lower value. We initialize a value for sum. We set up another for loop that goes through the range of our upper and lower plus 1. Remember plus 1 here because we're going to need to actually go up to the next value in the list in order to get to the last element. And then we just update it by taking each consecutive value and adding it into the sum. So it'll iterate through this for loop. And every time we increase I, it just increases the sum, or it may decrease the sum in the case that the element of Li is a negative number, of course. All right. So once we're done with this for loop, we go on to this max so far. We're going to compare max so far and sum and take whatever is maximum. So if that sum is bigger than the max so far, it gets replaced. And then it just returns the max so far once we've iterated through the full range of the length of list, and then the range from the lower up to the length of list. Of course, that's our nested loop there. Okay, so what's efficient, what's inefficient? Well, we're using nested loops here, which if you can avoid nested loops, of course you want to do that without a doubt. We have, in fact, 3 nested loops. So I think we can improve things in the next approach. So how many times does approach A have to compute the sum 1, 2, 3 in the above list? Well, let's think about it. Let's go through. It's going to go through first. You start at 0, where it's going to compute it 2 times with your lower value being 0. So 2 times, keep track of that in your head. Then our lower bound becomes 1. It'll compute it 2 times there. Okay, then our lower bound becomes 2. It will no longer compute 1 plus 2 plus 3, right? Or when it's 3 or when it's 4, because we've gone beyond the lower bound of 1. Okay, so it's a total of 4 times. Probably unnecessary. Okay, so this approach is well named. It's not a great approach. It's the awful approach because it's going to be the slowest. To find the sum segment here, you had to compute this, but in order to get the next one, you had to compute the same value again. Why are we having to redo that work again? You probably want to avoid trying to do that. So in general, when it sums the elements between bounds, the lower bound and the upper bound, L and U here, we'll repeat all the work that we previously did by finding the bound of L up to U minus 1. That's not good. That's not efficient, okay? The second approach is going to compute the sum of a segment by adding only the rightmost element. So right there, we're going to see an improvement. I'm going to stop the video here and pick back up with that second approach.